All right, continuing on with week 5. This is another example for the Exam 1 review session. This is coming from Mirovich's Fundamentals of Vibration. So we have a rigid body and we have all the information that we need. The mass is equal to 1,750 and it's all concentrated at the mass right here. The damping is 3,500 newtons seconds per meter. The stiffness is 7, let's call it E5 newtons per meter. These parameters are A is equal to 1.25 meters and B is equal to 2.5 meters. And we're trying to find the critical damping. So let's draw our free body diagrams. Good place to start. I'm going to displace it this amount right here. Okay, so here's my FBD. And, I don't really need all this other stuff up here. I was just thinking my way through it and speaking it, so I'll clear my way with my IBD. So these two things are equal to each other. And let's put up the loads. So I'm going to call this point O. So this is Roy. And this is rocks. We will put in gravity, which is green. So there's mg happening right there. And we'll put in, I guess I'll put a spring force right here, Fs. And then we will also put in a Fd for this damper. I think that's all we need. We will also, so we'll make this assumption that we're moving in that direction. And that's going to cause an acceleration here. And so this is going to be m. And we had to have b times theta double dot, right? So that's the tangential acceleration. And we might as well draw in a normal acceleration, even though it's going through the center, right? Whoops, come back out. Where did we go? How do we do that? Go back. I really messed this thing up. Let's see, go back, go back, go back, go back, go back. There you go. All right, so what else am I doing here? Do I want to put a little green? No, we'll put a light green in there. And here is our angle that we're working through. So one thing I could do as part of this, as a side note, and I didn't do it when I did this example in class, is draw the equilibrium FBD. All right, so this is a statics thing going on here. And we can also put the Roy and the rocks. And so the only forces that we have coming on here is we're going to have a spring, Fs, and maybe I'll write St for being static. And we have mg right there. We don't have a damper force because the damper force is dependent on theta dot, and we don't have a theta dot. So what we can have here is we're going to have the sum of the moments about O is equal to 0. Counterclockwise is positive. So you're going to have, and by the way, this is going to be equal to K times, we're going to assume that if in the pre-stretched position, we would have had up to right here. Okay, so there's a deflection. There's an initial deflection right there that we could call it, I guess we'll call it I'm trying to think if I want to if I want to do the del and or if I want to do the thing. So we could actually just call it here. Here's our static deflection. Okay. So what you're left with is K times del static deflection times A, and then minus mg times b, and that equals to 0. So what we're doing right here is something I'm totally okay with neglecting, as long as you write out that you've ignored it, right? That you'll know. What our purpose here is basically when we have a spring that's in the vertical position, and we have a gravitational mg, which we always do, that for the static case, those two portions are going to disappear from this FB because of the static case right there. So let's try to make our way through there. I didn't write it out this way originally, so I'm kind of flying without a net right here. We don't have the mass moment of inertia of a distributed bar right here, because we're going to ignore mass. We're going to ignore the mass of the rigid bar. So what we have is the summation of moments about O as an effective mass, and as an effective moment. So when we come through here, I should have over to the side written that Fs of the spring, excuse me, is going to be K times L theta plus del st, right? That's because it has not only deflected L theta, but it already has a pre-deflection of that right there. We'll also say that the damper is going to be C times B theta dot, right? Because that's going to be the velocity here at that spot. So coming back to our equations here, counterclockwise, we're going to have that spring is going to go in counterclockwise, and you're going to have L theta plus the static plus the moment arm, which is going to be times A. Then we'll also have the damper, which is going to be positive, and it'll be C times B times theta dot, but that's the force, the damper force. We also need times B again for the moment, so that's squared. And then we have equal to, is going to be in the clockwise direction, so it's going to be negative mb theta double dot, but that is the inertial force, the effective inertial force. We need the effective inertial moment. We multiply it by b again, so b squared. Let's do another step here where we take the KL, I said L, excuse me, I'm sorry. Right there, let's go A, sorry. So there's A theta times A, so we're going to have A squared theta plus K, I guess I'll go K there times A. Oh, damn it. Okay. I forgot. Put the moment in. I'll fix it here in a second. So that's minus mg times b equals negative m, and then we go b squared theta double dot. Okay. So I'm going to move this minus mgb right to there, and then so it jumped over. cb squared theta dot equal to negative mb squared theta double dot. And just as we've seen before, but we haven't done it in a little while, that's why I'm doing this, we'll see that this guy right here is equal to 0, so we can ignore him. So we could do that quite often, but it'd be good to emphasize why we did it, right? So in this case, we don't have to write down what we did, but if we ignore it, we'll write down that we are going to like ignore or something along the lines that it cancels out. But it only cancels out if it has this arrangement where the spring is vertical right in there. You know, this one works too. If there was a spring like that, we would do this whole thing, and then it would cancel out to the thing. We could just write down that we know it and why we did it, and so we don't need to go through this whole process every time because we know it. So here's what the equation of motion that we would write of the thing goes: mb squared theta double dot plus c b squared theta dot plus k a squared theta equals 0. All right, so another way to write this, the equation of motion, is to get this nice and clean by getting that over here. Now you'll notice that this b squared is going to go away. So let's just not even write him. All right. Plus, and they go k a squared over m b squared. All right. I think I got that. Let me double check what I've got here. Okay, so either one of these we could call the equation of motion. This is probably the easiest one to do. So, but we want to find the critical damping value. So let's go ahead and substitute theta equals e to the lambda t. We could call that the characteristic equation. I think sometimes they mean this is the characteristic equation. We go lambda squared plus that whole thing. Did I just jump? Oh no, I did a c over m. Let's see, my other computer wants to know if I still want to continue working, and the answer is yes. Lambda plus k a squared over m b squared equals 0, and then we want to find the roots. So we use the quadratic equation, two separate roots here, negative c over m, but we have a 2, right? Because it's, you know, the quadratic equation is is that we have b, negative b, plus or minus the square root of, b squared minus 4ac over 2a, right? But a is 1 in our thing right there, so that's why we have a 2. This 2 right here comes back up onto the top, and we go plus or minus the square root of b squared. So we have c, but we need that 2 in there again because of that 2. Ends up coming up in there, and that's squared. Minus, and we don't need the 4, once again, because of that 2. And we don't have an a, so all we do is write this guy. Right? And so what we were trying to find, remember, is the critical damping. Critical damping, so it's critical when equal to 0. So we could say that c over 2m squared minus k a squared over m b squared. So we have c equals to, and equal to 0, sorry, 2m square root of k a squared over m b squared. So c is going to be equal to 2 times 1,750 times the square root of 7e5 1.25 squared over 2.5 squared and 1,750. All right, so we did all that right, correct? And we get a c is equal to, oh, by the way, that's cc. I should have made that cc, because this, we could start calling this cc because this is the critical value. 35 35,000. Someone planned this out so it would come out to even number. So there you go. There's the critical. If someone were going to ask, well, what's the damping ratio right here? We get C over CC. And we would say that we have 3,500 over, because if you go back up to here, you'll see we had 3,500 over 35,000, which is not hard to do, right? So this is equal to 0.1 if someone were asking that. And that's not a bad problem to ask, I think. It's a pretty legitimate one. This is definitely a fair game. It's a 15-minute problem. That's a lot. So we could probably have sped up if we didn't ask to do that, and I'm not asking you to do that, so we could just write down that we had cancels out with statics. I don't know a better way to write it. Maybe there's a better phrasing onto the thing. But that's what this means right there, that it will cancel out due to statics, and you would have saved yourself definitely a couple minutes, maybe 3 minutes, so then it turns into a 12-minute problem, which isn't too unreasonable. I will do the next video.